Okay, in the previous class we saw what is a failure. It's a mechanical change in size, shape or material properties of a structure. Okay, and that renders a machine incapable of satisfactorily performing its intended function. Then we saw what is designer's objective. The objective is to have or design a product which functions for a prescribed lifetime and also competitive in marketplace. And then we also learnt about what are the duties of our objectives of a designer, or recognize the potential failure modes, acquainted with array of failure modes in in-field and conditions leading to such failures, and you should have good working knowledge of analytical or empirical techniques of predicting failure. So thus failure analysis, prediction, prevention are critical to any designer. That's what we saw. Then we saw the definition of design, and also the optimizing the design is with respect to performance, life, weight and cost are all these. And what are the challenges for a designer? Or the rotational speeds of shafts may exceed 30,000 rpm, operating temperatures may be in excess of 2000 degree Fahrenheit, there can be nuclear environments and so on. Then we learnt about the major objectives when designing. So all parts should be capable of transferring necessary forces, performing necessary functions. Failure must not occur prematurely. That means it should run for the predetermined time. Each part must perform its function without interfering with any other part of machine. Weight and space should be inconsistent with application. That means it should not be too bulky. Possible to service and maintain. That is, all the parts of an automobile or a machine we should design such a way that it is accessible, the parts are accessible for service. Then it must be competitive in market and profitable for manufacturer as well. Then we learnt about the failure modes. Two failure modes are body type and surface type. And then failures can be fatigue failure or because of corrosion, which are unilateral phenomena. Then it can be corrosion fatigue, which is a combined phenomena. Then we learnt about the failure inducing agents. Basically there are four failure inducing agents as we saw. One is the force, time, temperature and reactive environment. So in force we learnt about steady, transient, which lasts for short time, cyclic, random and short time, and then temperatures, various temperature and reactive environment. Then we learnt about modes of mechanical failure. Modes of mechanical failure. So then after that we learnt about classification of failure mode prediction. It can be, so four manifestations of failures are, it can be elastic deformation, plastic deformation, rupture or material change. Then we learnt about various types of failures in practice, and this is what we learnt in the previous class. Then moving on to the next part of our discussion is the review of static failure theories. Before we get into static failure theories, we should learn a bit about Mohr's theory. Okay, Mohr's theory is what we need to learn about a bit. Now we can take an element of a member which is subjected to multi-axial loading. I just take this as an example. So this is an element of a body which is subjected to biaxial or triaxial stress system of 20 megapascal in x direction, 90 megapascal in y direction, and it's also subjected to a shear stress of 60 megapascal. So we need to find out, for such a combined loading, we need to find out the maximum principal stress and maximum shear stress by using Mohr's circle method. Okay, Mohr's circle method we can use and find out the principal stresses sigma 1, sigma 2 and maximum shear stress tau max. Now we have sigma x to be equal to minus 20 megapascal, then sigma y is equal to plus 90 megapascal, and then we have tau xy given by plus 60 megapascal. This is what we have got. So for construction of Mohr's theory, Mohr's circle, select any point, okay, call it as maybe O. Since my sigma x is minus 20, I travel to the left of this any selected point to some suitable scale by a distance of 20, that represents sigma x is equal to minus 20 megapascal. Okay, maybe I call that point as some A. Then I have sigma y as plus 90. So from O I travel to the same scale, I travel to right, okay, for a distance equal to 9 megapascal. So therefore this represents sigma y to be equal to 90 megapascal. I call this as some point B. Now what we need to do is, from point A, I have tau xy given by 60 megapascal. So from A you travel vertically up, and to some suitable scale, it is a representation of shear stress to a height of 60 megapascal. From point B, travel to that scale again by 60 megapascal. I call it as some point M. Now bisect line AB and locate its center, call it as some O dash. Okay, so through O dash, M, and this point I call it as N. So through M, passing through O dash, and then join it to N. Okay, then with O dash as center, O dash M as radius, draw a circle. Draw a circle which passes through M and N, and this is called Mohr's circle. Okay, now we need to find out the value of sigma 1 and sigma 2. So from O, you extend the line OA. From O dash B, extend this line till it touches the Mohr's circle. The distance from O to the end of the circle. So this distance will give you the value of sigma 2, that is minimum principal stress, that is around 48 megapascal is what you get. Then from O, draw a line to the end of the circle. Maybe I call it as L, and so O to L distance will give you the value of maximum principal stress, that amounts to around 117 megapascal in this case. Okay, now to find out tau max, the radius of Mohr's circle will give you the maximum shear stress value, that is this distance will give you maximum shear stress, and in this case it is found to be equal to 81.4 megapascal. Is it okay? So this is how we draw Mohr's circle and find out maximum principal stress, minimum principal stress, and maximum shear stress. So this is about Mohr's circle method of finding out the principal stresses when a component is subjected to multi-directional loads, or it is also called combined loading. Combined loading, when it is subjected to, then by Mohr's circle method we can find out the maximum, minimum principal stresses and maximum shear stress value. This is about Mohr's circle, which we need to know before we get into review of static theories of failure. Okay, now let's look at the static theories of failure. Now if you look at, let's review the static failure theories. Parts will fail. Is it because of tensile stress? Is it because of compressive stress? Or is it because of shear stress? That we need to find out for a combined loading case. So here if you see, this circle represents the Mohr's circle for tensile test. Okay, and this is for torsion test specimen. After that, then in general, as we have seen, ductile materials are limited by shear strength, whereas brittle materials are limited by their tensile strength. And now to correlate between the test results that are obtained and the components in the practice are subjected to combined loading case, okay, the theories of failure will bridge the gap or will give a relation between the yield stress that is obtained in tension test and the component in actual practice which is subjected to combined loading case, they'll give a relation. A relation is given by the theories of failure between the component that is tested under tension test and the component which is subjected to combined loading case in case of practical applications. So what are these theories of failure? What are the various important theories of failure? Or the maximum normal stress theory or Rankine's theory, maximum shear stress theory, maximum normal strain theory. These are the theories of failure that we have studied in our DME 1 itself in 5th semester of BE. Then you have got total strain energy theory, distortion energy theory, or it's also called Henke and von Mises theory. Then you have got Mohr's theory and modified Mohr's theory, or it is also called Coulomb-Mohr's theory. Now, in general, let's look at the general framework for definition of these failure theories. Failure is produced or predicted to occur when the maximum value of selected modulus. In case of maximum principal stress theory, it's going to be the maximum principal stress sigma 1 in a multi-axial state of stress becomes equal to or exceeds the value of same modulus that produces failure in tension test specimen using same material for specimen. This is the general framework for failure theory. That is, when it is applied to maximum normal stress theory, failure is predicted to occur when multi-axial state of stress, when maximum principal stress, that is maximum principal stress becomes equal to or exceeds maximum normal stress at the time of failure in a simple uniaxial tension test specimen of the same material. That is, the failure would occur when the maximum principal stress sigma 1 becomes equal to or greater than yield stress by factor of safety. The failure would occur. Okay, this theory is suited best for brittle materials. Next, maximum shear stress theory. Here, the failure of a component would occur which is subjected to the multi-axial stress state. Failure would occur when the maximum shear stress becomes equal to or greater than the yield shear stress. Okay, then the failure would occur. This is according to maximum shear stress theory. So that is, when tau 1 becomes equal to tau y by factor of safety, okay, then the failure would occur. And then we know that the shear stress is equal to half of normal stress. That is the yield shear is equal to half of yield stress, okay, of the material. This is about the maximum shear stress theory, and it is very good for the ductile materials. Okay, and then when you plot it, it will be in the hexagonal form. So within the region, when the values are within this hexagon, then there is no failure occurring. Any value which falls beyond this, then the failure would occur. This is the failure region. This is no failure region. That is, when tau 1 is less than sigma y by FOS, then failure will not occur, which is inside this hexagonal representation. Any value that falls beyond this tau 1 is equal to tau y by FOS, then the failure would occur. So this is according to maximum shear stress theory. Then comes another not so useful in practice. One is maximum strain theory. Another is a total strain energy theory, where total strain energy per unit volume becomes equal to or exceeds total strain energy per unit volume at the time of failure in a simple uniaxial stress state. So this is according to total strain energy theory. And then we will go to distortion energy theory, which is very useful in practice. So according to this, failure is predicted to occur in multi-axial state of stress when distortion energy per unit volume becomes equal to or exceeds distortion energy per unit volume at the time of failure in a simple uniaxial stress test using specimen of the same material. Okay, so total strain energy is divided into two parts here. One is called the dilatation energy and another is called the distortion energy. So under conditions of ductile behavior, it is postulated that failure occurs because of only distortion energy with no contribution from dilatation energy. Normally dilatation energy is associated with a body submerged in water which is subjected to pressure in all directions. Next. Now let's look at the failure of brittle materials. So here brittle materials fracture rather than yield. As we know, the brittle material does not have any yield point. Now let us look at what are even and uneven materials. So materials which have got equal strength both in tension as well as compression, such materials are called even materials, whereas in case of materials such as grey cast iron, so they will have high compressive strength but less tensile strengths. Such materials are called uneven materials. So by Mohr's circle we can represent that for an even material, if you see the even material, both in tension as well as compression they have same strength. So therefore these two circles are of same diameter. Okay, when it is the case of uneven material, if you see in case of, say for example, grey cast iron, its compressive stress is much more compared to the tension strength or tensile strength. So such materials are called the uneven materials. Stop.